This is Module 3, first video. We're going to discuss the first page of the lecture guide, which is discussing the idea of p-value. P-value is a value that we are going to use for the rest of the semester as a value that helps us understand the strength of evidence that we have against the null hypothesis. Another way to say that is saying the strength of evidence that we have in support of the alternative hypothesis. So let's begin. P-value is defined as follows. Assuming the null hypothesis is true, the p-value is the probability of getting a value of the observed statistic or more extreme. So before I go on to the next part, let's think about what that means. As we learned in the last module, the first step in our 3S strategy is that we find an observed statistic out in the world. The second step is we simulate. We create a null distribution. That null distribution is the set of sample statistics that we expect to get if the null hypothesis is true. So this is the null distribution. It's the distribution of sample statistics we expect to get if the null hypothesis is true. Notice that means we are assuming the null hypothesis is true when we build this null distribution. This null distribution is centered at the hypothesized value of the parameter from your null hypothesis. So it'll either be centered at the pi from your null hypothesis, or it will be centered at the mu from your null hypothesis. About half the expected sample statistics will be above it, and about half will be below it. So we got an observed statistic, we simulated to create this null distribution, and now the third step is finding strength of evidence. So far in the course, what we've said is we've kind of been a little wishy-washy about it. We've said if your statistic turns out to be kind of up here in this area where there are not many dots, or there are no dots, or if your sample statistic kind of comes out down here in this area where there are no sample statistics, or just a couple dots. Then if it comes out in one of those tails, the left tail or the right tail, if that's where your observed statistic was, then you conclude that you have a lot of evidence against the null hypothesis. You have a lot of support for the alternative hypothesis. If your observed statistic came out here in the area where you see a lot of expected, normal, and usual sorts of statistics, then you would say that you think the null hypothesis is plausible. So instead of being so kind of wishy-washy about our conclusion, what we're going to do is we're going to add what's called a p-value to this, where we actually put a numerical mathematical value with our conclusion, with our strength of evidence. Okay, so again, let me read this one more time and kind of put that together with what we've learned. It says, assuming the null hypothesis is true, the p-value is the probability of getting our observed statistic or more extreme. So it's saying if the null hypothesis is true, then this distribution shows you what sample statistics should look like. You then locate your sample statistic on here. The p-value is the proportion of sample statistics that are like your sample statistic or more extreme. Basically, you will count the dots that are like your sample statistic or more extreme, and then divide by the total number of dots. So the p-value, you count the dots that are like your sample statistic or more extreme and divide by the total number of dots. Again, the dots here are in your distribution, the dots. But remember, the dots represent the sample statistics we expect to get if the null hypothesis is true. So you're counting samples that would be like yours or more extreme out of the total. It's giving you like a probability of getting a sample like yours if the null hypothesis were true. All right, so here in this first bullet point, it kind of describes that for the three different ways you might write an alternative. If you have an alternative hypothesis where you use a greater than symbol to say more extreme, means you're counting dots that are like your sample statistic or higher. The alternative reads higher, so you count sample statistics that are like yours or higher. If your alternative hypothesis is that the parameter is less than, then when you're finding a p-value, you'll count sample statistics that are like yours or lower. And if you have an alternative where you have a not equal to symbol, you're going to actually count on both sides. This is called a two-sided test. These other two up here were one-sided. You're counting dots on one side of the null distribution. When you do a not equal to symbol, you're going to count dots that are like yours and more extreme, meaning, for example, if you had this null distribution and your sample statistic were right here, your p-hat were right here, you would count the sample statistics that are like yours and higher, and then you'd go to the other side of the distribution. You would find this distance that matches the distance from your sample statistic to the middle, and you would do the same distance on the other side, and you would make this line right here, and you'd say, all right, I'm also going to count the sample statistics that are like this and lower, so like mine and higher, and on the equal side, on the other side of the distribution, like that and lower. All of those are as extreme as yours. All right, so how to find it with a computer simulator. So one way we might ask you to find this p-value is when I give you an actual distribution, and you're asked to actually count dots and calculate the p-value. Another way you might be asked to find a p-value, which is actually more common, is you'll use the computer simulator. In the computer simulator, you are going to use the count box in the computer simulator, and you're basically going to make the computer do the same thing. You'll tell the computer to count the number of dots that are like yours or higher, or count number of dots that are like yours or lower. You'll have to pick less than or greater than, or if it's a not equal to, you pick the two-sided button, and then you put in your sample statistic and have it count. And we'll do that in some of our examples in the next couple videos. How do you make a conclusion from this? Well, if you have a smaller p-value, that means you have stronger support of the alternative. You have stronger evidence against the null hypothesis. Small p-values mean a lot of evidence. Again, going back to this null distribution up here, if you have this null distribution, if your sample statistic were, say, right here, that seems kind of like evidence against the null. It's sort of out in the tail. There are not too many dots like yours or more extreme. However, if your p-hat were further out in the tail, say out here, there's even fewer dots like yours or more extreme. This would be a very small p-value. In my little drawing, it looks like there's only one dot out of the total that are like my sample statistic or more extreme. That's a tiny p-value. So the smaller my p-value gets, the further my statistic is out in the tail, the further it is away from the null hypothesized value of pi. So the further your statistic is away from the null hypothesis value of the parameter, the smaller your p-value. That's a very, very important concept in the class. Smaller p-values is more evidence against the null. Smaller p-values is more support of the alternative hypothesis. And then likewise, bigger p-values is more support of the null hypothesis being plausible. Again, back to the null distribution picture. I have this little null distribution here. If my sample statistic were, for example, right here, and I were counting samples that are like my sample and more extreme, I'd be counting all these dots. That's a lot of dots. That would be a big p-value. There's lots of samples that are like mine and more extreme. So that is saying, it seems like the null hypothesis may be plausible. Look how close my sample statistic is to the hypothesized value of pi. Seems like that pi hypothesis could be plausible. Big p-value means our null hypothesis is plausible. Small p-value means we have a lot of evidence against the null hypothesis, a lot of support for the alternative hypothesis. All right, lastly, Now, these are the chapter 1 from your textbook number values that they kind of give as cutoffs for how you should start thinking about the actual numerical values and what kinds of conclusions you should say. First of all, note a p-value has to always be a number between 0 and 1. Because it's a proportion of samples out of the total number of sample statistics in the distribution. It's got to be either 0 dots like this or more extreme, all the way up to 100% of the dots are like this or more extreme. And that can't be negative, and it couldn't possibly be more than 100% of the dots. So it's somewhere between 0 and 1. Then the textbook kind of breaks it down into 3 other intervals in which you have some language that they offer you when you're writing your conclusions. First, your p-value may be a value between 0 and 0.01. So this is between 0 and 1%. So between the percent of sample statistics that are like yours or more extreme is somewhere between none of the sample statistics up to only 1% of the sample statistics. This is a very small p-value. So this is very strong evidence against the null hypothesis. It is very strong evidence in support of the alternative hypothesis. The next interval range that the book discusses is the range from a p-value of 0.01 to a p-value of 0.05. So we're talking 1% of the sample statistics up to 5% of the sample statistics are like yours or more extreme. And that's still pretty small. And so we would still say you have strong evidence. We're just not going to use the word very in chapter 1. Very strong evidence is reserved for p-values between 0 and 0.01, and we'll use the phrase strong evidence when we're talking about p-values between 1% and 5%. P-values bigger than 0.05. Your book actually has another range where they talk about p-values between 0.05 and 0.1 and call that moderate evidence. I actually prefer to just say if it's bigger than 0.05, we're going to go ahead and usually say the null hypothesis is plausible. It's not statistically significant evidence against the null if it's a p-value more than 0.05. Null hypothesis is plausible. You don't have statistically significant evidence in support of the alternative. Likewise, then, we do say generally out in the world, when you have a p-value below 0.05, that is usually okay for us to say you do have statistically significant evidence in support of the alternative hypothesis. Please be sure to watch the next few videos where we're going to go through examples of all this.